Hello, this is Rick Powers. I'm making a recording of Basic Statistics Lesson 17. Hello, this is Instructor Rick Powers from Western Technical College, Basic Statistics. Lesson 17, Binomial Distribution, Part 2. Review. Binomial probability is based on measuring the number of successes, using the symbol X, out of a set of observations, using the letter N, when we know the probability of an individual success, usually the letter P. Examples include the number of coins that would be heads and the number of students that would respond yes when asked if they like soccer. Since the purpose of statistics is to know what to expect, we want to use binomial probability in order to predict what might happen when we conduct a survey. There are two ways to use binomial probability. Number one, compare probabilities to 5%. And number two, to use the empirical rule. The first method is shown in this graph. With the given values of n and p, we expect to have between 4 and 11 successes. If there were 0 to 3 or 12 or more, we would be surprised. It's a graph of the probabilities of the binomial distribution. N is equal to 25, p is equal to 0.3. There's a line going across at 0.05. So we see on the horizontal axis that the values of x, which are below 0.05, would be 0, 1, 2, 3, and then 12, 13, 14, 15, and so on. However, this is not exactly correct, since the sum of the low probabilities is more than 5%. It would be more accurate if we only allowed a total sum of 5% on the left and the right. Recall the definitions used in the empirical rule. If we define an interval using the mean plus or minus 2 standard deviations, then we would expect 95% of the data to be in that interval. Also recall this is only true of bell-shaped data. This might work for us because it looks like the probabilities of the binomial distribution may be approximately bell-shaped. But we need the mean and the standard deviation. As it turns out, the mean and standard deviation of binomial probability are not difficult to find. Here are the formulas. Mu, the mean, is equal to n times p. Sigma, the standard deviation, is equal to the square root of, inside the square root, n times p times 1 minus p. And oops, I've got an extra parenthesis in there. As before, we can also use technology to find these numbers. However, the idea of being bell-shaped is not always easy to determine. Some binomial distributions definitely are not bell-shaped, while others definitely are. So we see a graphic of some different examples of binomial probability distributions. One is not symmetric, it's skewed to the right. The other looks kind of bell-shaped, and then the third is definitely bell-shaped. Those who work in statistics have come up with a formula to describe when a binomial distribution is close enough to be called bell-shaped. N times p times 1 minus p is greater than 10, or the standard deviation is greater than approximately 3. The first inequality is the official one. There are a couple of very important concepts to consider for this. First, it is important to keep in mind what is being measured. When we say the mean is 7.5, that is saying if we did a lot of observations of a specific size of group, then we would average 7.5 successes. Also, the idea that the data is bell-shaped when the standard deviation is greater than 3 only applies to binomial probability. If we are talking about measuring some other type of number, then the shape of the distribution of data is not determined by the value of the standard deviation. If we take our example of asking 25 students about liking soccer, n is equal to 25, with a general probability of 0.30, p equals 0.30, then we get these results. Mu, or the mean, is equal to 7.5. Sigma, the standard deviation, is equal to 2.3. This is not quite bell-shaped according to the formula, but the graph is pretty close to being bell-shaped. One example where this idea is useful is the context of a political survey. Let's say we have a national poll that shows support for Joe Biden as president to be at 53%. If we have a survey of 600 people, what would we expect to see? When we have relatively large sample sizes and the percent is close to 50%, then we will get bell-shaped results. In this case, the standard deviation is 12.2, so we're fine. And the mean is 318. So according to the empirical rule, we would expect anywhere from about 294 to 342 people to support Joe Biden out of 600. If we translate those numbers back into percentages, that means we could observe results anywhere from about 49% to 57% and not be surprised. So if I look at polls of 600 people, I should allow results to be within about plus or minus 4%. There are many, many factors that affect polling results and their connection with voting results. But I hope you see that polling cannot tell us exact answers. Even if we assume that everyone's the same, the results can be either above or below the true or the general probability number. Note, there are organizations who work with polls that use complicated methods to work with the results in order to gain better understanding of what to expect. I follow 538.com for many results. But it's really important to emphasize what happens in this process in measuring treatments for heart conditions or the effect of laws about guns or anything else. The variation in a measurement of percent must be considered when basing decisions on such measurements. End of lesson 17.